Okay, so as I said, today we're going to have a different projector as normal, so I might inadvertently point that way and be pointing at nothing. It's just force of habit. This wasn't working for some reason, this projector. Today we're going to talk a little bit about convolutional and recurrent networks. And this is going to be a little bit more high level of a lecture, certainly than the last time. It's going to be a little bit more about, because we can't dive into too much of the details about convolutional and recurrent networks all in one lecture. But in some sense, this is actually why, these types of networks are actually why deep learning is currently exciting. So although deep learning, kind of the mechanisms work like we talked about last time, the actual successes of deep learning have all come through these convolutional and recurrent architectures, and they're really what's driving the current interest in deep learning and in some sense in AI as a whole. So we'll talk a little bit about these. And give you at least some sense of how they work in the context, though, of backpropagation, which we talked about last time. So we'll start off particularly talking about convolutional networks. We'll then talk about some of their applications, and we'll talk more briefly about recurrent networks and some of their applications. So hopefully we'll get through all of that. If not, the slides themselves can kind of have some nice pointers to additional material you can look at. All right, so let's jump in and start talking about convolutional neural networks. Now, as I said, these networks were the genesis of this surge of interest in deep learning. So I mentioned the AlexNet architecture. That was a convolutional neural network that was trained to perform well on this ImageNet classification problem. And I think it's not too controversial to say this kind of spawned or reignited interest in deep learning, despite the fact that the actual techniques for these things go back almost 20 years now. So despite the fact that they're very old, these are really what has driven, in some sense, the surge of interest in deep learning. So what are convolutional networks? Well, if we think about how we can apply deep learning or neural networks in general to sort of large, higher dimensional inputs, we start to come up with some problems. So in particular, if we think about something like a 256 by 256 color image, that would have 256 by 256 pixels times 3 colors. That's about 200,000 inputs, dimensions. If you think of that like a big vector, that's about 200,000 different inputs. And so at the very least, if you're going to have a network that is going to classify these things, you need this many units times the number of classes you have, just for a linear classifier, right? And that's already actually a pretty big number. Already, it's going to be pretty hard to actually come up with an architecture that won't just overfit to your data, right? Because we know that the number of parameters, that's how it sort of expresses your function is. And if you have that many inputs, you're going to be able to fit anything in training data perfectly well, and you're not going to generalize very well to your test set, though. And the other sort of problem here is that there are a lot of what are called invariances of images as a whole that aren't really well captured by this, right? So say, for example, now that I want to not just have even a linear architecture, I want to have like a multi-layer neural network. And I'm going to draw my input here as kind of a plane of all the pixels in the image. And I have some hidden unit here. And I'm going to also drawing it as a plane here, or as a picture here, though, of course, it doesn't really have to be a picture in the fully connected setting. But in a deep neural network, the way sort of the connections work, right, is that we think of that input as a big vector, and we think of the next layer as being some matrix vector product, right? So that what that means is that every single pixel in the subsequent layer can depend on every single pixel in the previous layer. Of course, they would really do it through this wx plus b, w times x plus b, all up with a nonlinear function applied. But you can sort of think of it just because w here can be dense, you can think of every pixel in the previous layer having an impact on every pixel in a subsequent layer. And that seems kind of wrong, right? Because we sort of think of images as being kind of having certain invariances. Like if I take my character and I move it 1 pixel over to the right, this shouldn't entirely change the classification here, right? You think of these things as being related somehow, but that wouldn't quite work. And this network doesn't actually encode that, though. So there seem to be these kind of problems with using a dense representation for things like this. And so what this leads us to, if we start thinking about how we can restrict the set of allowable spaces here, this leads us very naturally to an architecture that's known as a convolutional neural network. And the idea is very simple, actually, though we'll talk about convolutions a little bit more in a second. The idea is kind of very natural in some sense. What we're going to do is really two things. First of all, we're going to require that the activations, sort of the values in the second hidden layer, depend kind of on or a subsequent hidden layer at least, if these are sort of arbitrary layers in our network. That first of all, they depend only on kind of a subset of the activations, the values of the hidden the hidden states in the previous layer. This is going to kind of be a local subset, right? So you think of like this pixel in the top right, top left of the hidden layer. That should only depend on kind of the top left-ish pixels in the previous layer, right? So we're thinking of them actually as images now, not just as big vectors that have some values. And that in turn is going to actually make us, and after that we're going to impose some of this sort of locality structure on the network itself. The second big thing we're going to do is we're actually going to share the weights between these different regions. So what that means is we think of kind of one set of weights here being the weights we apply to those pixels in the first image to get that value in the second image. And that actually is done through a convolution, which I'll talk about in a second. But it really is just kind of a mini vector product here. So all those pixels there lead to that one pixel there, but multiplying them through the weights and adding them up. And we're going to require that actually every single block uses the same weights. So I'm going to apply the same weights to the top left group of pixels to get that top left pixel, then the sort of the middle top pixels to get that middle top pixel, etc. Right? So I'm enforcing the fact that we're going to have some degree of locality in our subsequent layers. And I'm enforcing the fact that they're going to share parameters. They're going to share weights. And as you might imagine, this is going to cut down on the number of weights we have enormously, while still kind of preserving a lot of the things that we want actually about a network. So we actually do encode kind of local features about the network. All right, any questions so far? I also kind of just jumped right in. So if you have any questions about what we covered last time too, feel free to chime in now. I didn't really give people a chance to ask that. Actually, I might pause here and also say that I think homework 2 is going to be out today. If not today, then tomorrow. But we're really shooting for today, so should be today. Yes, question.
What was the precise definition of activation?
Yeah, so that's a good point. So I'm using a lot of terms kind of a little bit colloquially here, which I apologize for, and they're kind of part of the nomenclature of neural networks. So activation usually refers to a value in a hidden layer. So it's just sort of the value one of these hidden layers, one element in the hidden layer takes on. Or you can think of actually the activations as a whole being actually just the hidden layers. They're just the values the hidden layers take on. That term activation comes from the neural terminology here. So activation is like what happens in the brain when something turns on. So I apologize for slipping into that. I just will. It's a common term in the literature, but I probably should have defined it. But yeah, activation just means a hidden layer. Yeah. I'm not showing here the nonlinear part, but there's a nonlinear part too. So we still have, in some sense, the overall function for our network, though I'll write it differently in a second. It's going to be something like this, like zi plus 1 is a function of some matrix wi zi plus bi, where this term, though, is a little bit different here. Because it doesn't quite fit that form. It's not a general matrix vector product anymore. It still actually can be written like that, but we're going to think of it kind of more informally as one of these convolutions. So instead of just taking a matrix vector product, I kind of apply this convolutional filter to Z, and that's how I get B. So let me actually just talk a little bit more detail about what convolutions are, because they're very simple. I should also say, I have this on the next slide, but if anyone's coming from signal processing here, you'll probably raise your hand and say that that's not a convolution. That's the opposite of convolution. That's a correlation. And you're right. For some reason, people in computer science, when they invented these things, didn't bother with the normal definition of convolution. So normally convolutions are the same thing, but the filter is flipped upside down and left right. But don't worry about that. We're just going to call this a convolution right now, and I apologize to all the EE people here because you're going to cringe while you keep hearing me talk about convolutions here. But this is the standard in deep learning, and unfortunately, that means the libraries are all inconsistent too, because we all call them convolutions, and then people in EE call them correlations. But the idea, anyway, is very simple. And in fact, convolutions have been around in computer science, and particularly in computer vision, for a very long time, much longer than deep neural networks or convolutional neural networks have been around. But they're a very simple operation. The idea is we have some set of weights, which I'll call a filter, and we have some image, which I'll call Z here, and then we have an output, which here I'll call Y, but in the network, that's going to be subsequent layers Z. This is a little bit easier notation here. And all we're going to do is we're just going to take my filter, take a patch of that size in the image, and we take essentially the inner product of those two things, right? So we take the product of all the corresponding numbers here, we add them all up, and that becomes a pixel in the output. Okay? And then we just slide this whole filter around the whole image, right? So we first do it here, that gives us the top left of the output. Then we do it here, then here, etc. You notice that the actual math here is changing very imperceptibly here, but it is changing. So this is just sort of the formulas for each different pixel in the output. But really, it's a simple operation here, right? It's just the inner product of this block and this block, that is the product of all the corresponding pixels, and then summed together. And really, these things have been in use for a very long time, as I mentioned, in computer vision. So for instance, convolutions, and this is convolutions, though, with pre-specified filters. This is not with learned filters, but this is with filters that are kind of designed, again, by a sort of an algorithmic designer. Those have actually been used for a very long time in computer vision. So it's very easy to sort of, and you can do this a little bit more formally mathematically, thinking about images as themselves kind of functions. But in practice, what this means is that a lot of sort of natural operations are easily specified in terms of convolutions over that image. So for example, if I take an image like that and I apply a filter like this, don't worry about that specific quantities there. That's actually a Gaussian distribution that it's scaled to have integer values, but then normalized so that it all sums up to equal 1. If I apply that to this image, that accomplishes something like blurring the image. So I basically am taking each pixel and I'm replacing it with an average of that pixel and surrounding pixels, which is a sort of a natural way of blurring the image. So it might not be that easy to see here, actually, but this middle pixel, this middle image here, is substantially more blurred than that image there. And you can kind of see that it's a little bit more fuzzy because I'm replacing each pixel with an average of its neighbors. Though this is, I think I mentioned this when I first talked about convex optimization. You actually can do the inverse process sometimes too. So you can actually try to find an image that when you blur it, when you apply a filter, it gives you something else. This is a common convex optimization problem. And it can actually do some nice things like nice denoising and stuff like that. They're also used in a little bit more complex cases, like finding what are called image gradients, or actually the magnitude of the image gradient, which is often the first step in like an edge detection algorithm. So what I'm showing here is actually something called, well, it's really called the magnitude of the image gradient. The image gradient is essentially how much the image is changing pixel by pixel. You can approximate that in the x direction by applying this convolution. So essentially, it'll look at the difference between these pixels here and subtract off the same amount of those pixels there. This is actually a difference, an image difference with a Gaussian blur also applied. This is called a Sobel filter for those that may have seen this before. But you can basically apply this one to get a approximation of the left-right change in pixels. And you apply this one to get an approximation of the up-down change in pixels. Then you square each individual entry there, and you take their magnitude. And that gives you a notion about how much the image is sort of changing in intensity at any given point. In other words, those actually correspond to edges in the image. So this picture here is what you get when I apply this operation to that image there. And these are very, very common things that have been around for decades in computer vision. And they're very useful in that context, right? They're sort of very nice ways of efficiently and quickly processing an image. All right, so what then are convolutional neural? Actually, any questions on that? Yeah.
For determining the size, like, I guess it's not specific on this, it's more specifically on convolutional neural networks. Are you going to go over how to determine the size?
A little bit. I'll talk about that a little bit, yeah. Very, and sort of a very high level, because there aren't great rules on that, honestly. It's much more about trial and error and seeing what works. But there are some rules. I mean, there is sort of post hoc justification about why people do what they do, but I think people didn't really know what to do until until they tried it out and they found some things worked. So we'll talk a little bit about that. All right, so the idea here, though, which you may be able to sort of glean from this, is that it seems plausible that convolutions, when also coupled with things like nonlinear operators, like these things here, right, of a particular form here, but in general, neural networks apply nonlinear operators too. Convolutions plus nonlinear operators seem to be able to capture some nice things about images, right? And so the idea of neural networks is that we're going to do this. We're going to do this within a network, but we're going to do it in a way where we actually learn what the filters are. Okay, so I actually had this equation later in the slide, but really what we're doing here is we're setting with again, a little bit of abuse notation here, because I'm going to talk about what we're really doing in a second. There are many dimensions involved here. But in some sense what we're doing is we're taking the next layer to be some function, some convolution applied to the previous layer, and possibly plus a bias. So this is what we're going to do in our convolutional neural network. But we're going to, just like a neural network, let these weights here, which take the place of a filter, that's the thing we move across the image, we're going to let those be the parameters of the algorithm. So we're actually going to learn those to kind of figure out what's the best possible convolutions we could apply to these images to kind of get the best information we can out of them to learn what's going on in this, in this set of images, or accomplish some classification task. And that's kind of the idea, the high-level idea of convolutional neural networks. Now, a few sort of details here, though. People do not usually apply sort of a single convolution layer by layer. What they're actually doing is they're actually applying multiple convolutions, and they're called, in some sense, kind of 3D convolutions, but importantly, they're really just summing over a big stack of layers here. So, for example, our input images in an RGB image are actually 3 by 32 by 32 if we have a 32 by 32 image, right? So we'll have something actually like 3 by 32 by 32 is the size of our image. And what we do when I say we apply a convolution to that, what I mean is that we actually apply 3 different convolutions, 1 for each different layer. That gives us 3 output images, and then we add them up to get the next sort of slice of the output layer. Okay, so the way I'm writing that here is that WI applies kind of to all those 3, but it translates to a single point in the next layer. Okay, so
this WI is the same for these 3 layers, right?
It can be different. So we apply potentially different convolutions to each layer, each slice, channel, there's something that's called because of the channels in RGB. We add them up and we get a single value. But again, we don't have to do this just one time, because the next layer also is multi-channel. So we actually apply this thing many times to get many different channels in the next layer. All right, so in some sense, and again, I sort of almost don't want to write this here, because I'm running out of indices here, and it just gets kind of confusing. But there's only 4, so everything is a 4-dimensional tensor at most here. They won't go too much further than that, just easy. But in some sense, you could write this as, and I don't have this in the slides anywhere, but for those that sort of care. Can everyone see this, by the way? I unfortunately am not, trying to move this a little bit. And I assume it's hard for the board to pick it up too. All right, so this is something like, man. All right, you can see the board now? Okay. So what this says thing really is something like, the, again, the jth slice on my I+1 layer is going to be equal to, let's see, how many indices I need? Let's just have one nonlinear function. Usually ReLUs here still works. Usually we take the max of it in 0 as our nonlinearity, the most common one at least. But really what that is this is sort of the sum from k equals 1 to however many channels the previous layer has. I'll just call that n. Again, I'm not using this notation anywhere, so just try to get the intuition here. Don't really care about the details of some filter. And I guess this filter should depend on I, because it depends on what layer it is. It also depends on which output you're talking about. Oops, I should have said z there first. So z, this is sort of the kth layer here of kth channel of the input layer, convolved with the wi, and I'll call it something like we need 2 indices here. We need like a j and a k, right? Because we need to index over both which input layer is it applying to, and then which output layer is it being applied to, plus b. And there can just be one bias for all of them. It's okay. So something like this. Again, don't worry about the details here. Just sort of know what's actually happening as we're taking all our previous layer. We're applying different convolutions to each element of it. That gives us, we adding them together, that gives us a single sort of slice in our next layer. And we do that however many slices we have in our next layer. Yeah?
Why do your hidden layers have to have so many sub-layers? Why not just have one hidden layer?
Yeah, so that's a good question. So why do we have to have so many different channels? And they're usually called channels. So why so many different channels? Channels are slices. I usually use the word slice, but I really should use the word channel. Why do they have to have so many channels? That's a great question. So if we just had one channel per hidden layer, then every subsequent layer would have to be a function of that, right? Which somehow seems kind of insufficient. In fact, it is insufficient because there may be multiple aspects of the image that we want to encode in different channels of the hidden layer, right? Because if we just remember, all subsequent layers are going to be only functions of this layer then, and then all subsequent ones are a function of that layer. So whatever information we don't capture in that hidden layer, we're throwing away. We're kind of omitting. And so in practice, you need multiple channels in each hidden layer in order to kind of encode different aspects of the image. It's very hard to interpret these things kind of qualitatively, interpret what they're meaning. But what you'll often find, for instance, is that certain channels will correspond to detectors for certain types of objects, for example. So a certain slice in a layer will have high positive values if there's like a dog in that part of the image right there, whereas another one will have high positive values if there's a cat in that part of the image, right? And so they, ideally correspond to kind of different semantic objects that are trying to be classified, but really what it comes down to is just encoding a lot of potential information that we sort of really need to keep around. Otherwise, we're just throwing too much stuff away. Yeah.
I think it's like your filters are 3D for or n-1 any of your channel of the previous layer. And the number of filters you have is the number of channels that you generate for the
Yeah. So you can think of the filters as being, yes, you can think of the filters as being number of channels by k by k, or k, I shouldn't use k, by filter size by filter size. And then the number of filters you have, yes, is equal to the number of output. Number of channels in the next layer, yeah. Yes, that's correct. But the important, there are only they're not really 3D in the sense you don't convolve ever over the channel layer, right? You only, like when I say 3D convolutions there, I'm putting it in quotes because 3D just means that I have a separate convolution for each channel, and I eventually add those together. Like I never convolve in the channel direction. I never like move my filter in that direction. Does that make sense? Yeah. Yeah.
So when we do a back propagation here, it's going to be affecting the gradient of the subsequent layer.
We'll talk about backprop in a second, because it seems really complicated, but it's actually not complicated at all. Kind of nicely. All right, so this is some additional, this supposed to say additional notes on convolutions. So as I mentioned here, and I always say this even before I have it in my slides, because I always get someone raising their hand who's an EE background that says, those aren't convolutions, you're doing it in the wrong way, and you're right. I don't know why we flipped them. I blame the computer vision people because they started doing it that way. We never really got the right terminology. And then by the time deep learning arrived, we were happy to do it incorrectly. So the convolutions are forever the wrong, the flipped convolution. So a few quick notes. In addition to that, it's also very common to zero pad the edge. So when I showed these things, right, I showed the next layer getting smaller than the previous layer because, of course, the valid regions there are. You only have, if your filter is size k, and your image is size n, you'll only have n minus k kind of valid regions where you have the entire space to convolve. So it's a little bit more common, because it's kind of hard to keep track of those things, of those dimensions, it's a little bit more common to zero pad your image before you do the convolution. So a convolution usually really refers to zero padding. You add some zeros around the sides of the image, and then you apply the convolution, and that sort of keeps your layers the same size from time to time, from layer to layer. So they all should all stay the same size. You don't shrink just by applying a convolution. And again, you'll kind of learn the right filters so that that's okay. So that the zero padding is okay, or you'll add whatever biases you need to make the zero padding okay. And then the last thing, which is also actually quite important here, is that the last operation that's very common to see here is what's called a max pooling operation. So a max pooling operation takes, and we'll do this actually for each channel in the image, it takes all the image, it takes something like a 2x2 block, takes the max over that block, and then whatever the max over that block is becomes the image, the sort of the image, the pixel in the next layer's image. So this operation will shrink your image down by a factor of 2. It'll make your image half the size because it takes blocks of 4x4 and makes them a single pixel in the next layer. Okay, now with these two layers, you actually now know everything you need to know to implement, a state-of-the-art deep convolutional network, in fact. Well, almost. You don't know how to do backprop yet, but these are the actual kind of the totality of operations. This, and then usually at the very end, a fully connected layer, are kind of the totality of the operations you need to actually achieve state-of-the-art performance in a lot of computer vision recognition tasks. So before we talk about backprop, which is what we're going to talk about next, I want to have a quick poll here, which actually I'm mainly just sort of curious if this even makes sense to people. So I will explain it. I'll ask it first, then I'll explain it, and hopefully in the explanation, if some of the sizing didn't make sense, it'll become more clear. So the question is the following. Suppose I have a convolutional network that's going to take input color images, so 32 by 32 by 3 channels really, and uses the following layers. So first it applies a 5 by 5 convolution where it has 64 different filters. That is, it outputs in the next layer 64 different channels. Then it uses 2 by 2 max pooling. Then it applies a 3 by 3 by 128 convolution. So that's 3 by 3 filters applied to however many channels the previous layer was. And then outputting in the next layer 128 channels. Again, 2 by 2 max pooling. And then a fully connected layer. That is, it takes all the remaining hidden layers, kind of can stack them all together as one big vector and applies just a normal, fully connected, matrix vector product here to get our output. So the question is approximately how many parameters would be in this network? Oops, I didn't want to do that. Oops, shouldn't show these guys yet. And by the way, parameter means a number, right? So each single element of WI is a parameter, considered a parameter here. All right, we'll do one more minute. The nice thing about this is they're all orders of magnitude, so you can just guess if you don't want to actually calculate it out. What feels right here for a... All right, we'll do 10 more seconds. If you're still thinking about it, just submit something. Okay, anyone need more time? Raise your hand if you're still like scrambling madly to, okay. All right, we're now going to say actually 10 more seconds, so just enter something. Again, just the actual fact that you answer is what matters here, not the answer you give. All right, I'm shutting it down now. Okay. All right. So, pretty even spread, but fortunately the mode is at the correct answer, or the approximately correct answer. So the more interesting question is, how do I actually come up with this, right? So A, is there even enough information there to tell me how many parameters there are? And there actually is, which is also something that's sort of useful to know when you're reading descriptions of networks. They'll usually specify it just kind of in that framework, and you will actually be able to tell how many parameters there are. So let's see how we go about actually doing that. Okay, so we know that we have our first layer, our first layer of our network, right? Takes as input 3 channel images of 32 by 32 and output 64 of them. So our first sort of layer will have 5 by 5 convolutions. So 3 by 5 by 5 by 64. That's our first layer. That'll have that many parameters. Max pooling does not have any parameters, right? It just takes the max of 2 by 2 grids and collapses into one. There's no parameters there. I'll also ignore the bias terms, by the way, because they will add a little bit to this, but not very much. So I'm just going to ignore them. they'll add basically, one pixel for each of the next size images. So, all right, so this is the first layer. That's that many parameters. After that, we apply a 3 by 3 by 128 max pooling layer, but that's going to be applied to all 64 channels of the previous layer, right? So it's going to be 64 by 3 by 3 by 128. Notice that nowhere in these layers does there any dependence on the size of the image here. So the size of the image is completely irrelevant because you apply the convolution with the same weights to the entire image. The size of the hidden layers will, of course, depend on the size of the images, but there's no dependence here on the size of the actual images in this thing. So now, though, I do have a dependence because now I'm going to have a fully connected layer where I take all my sort of remaining hidden units after this thing, stack them all together. So the question is, how big is that, right? Well, I have 128 of them. So I have 128 times the number of pixels that I have left, which is, I've shrunk it twice, so it's going to be, the remaining images are going to be 8 by 8. Because they're 32, I've cut them in half twice. 8 by 8 by 8. And then I have 10 final classes in my 10-dimensional output, so I'm going to multiply this by 10. So I believe that is around 160,000 parameters, if I did my math right when I was computing it. If anyone else did it and tells me that I'm wrong there, I could be wrong. But that's actually, this is correct. Whether or not the 3 is correct is to be seen, to be verified at least by everyone here. Does that make sense, how I arrived at that, and sort of what dependencies there are on the number of parameters in different layers? And in fact, it's quite useful to think of each of these layers as being, in fact, a sort of a block, a multidimensional array that has 4 components, or you can think of it as a rank 4 tensor, but they're not tensors in the real sense of actual tensor math. They're just multidimensional arrays. Tensor just sounds cooler, so people use the word TensorFlow and stuff like this. But really, this is sort of the way you think about storing these parameters usually, is as these kinds of blocks here. The last one you might sort of store as a big matrix, though, where you just flatten all these 3 dimensions. All right. So now let's talk about that's sort of how you compute convolutions. Let's talk about learning with convolutions now, right? This is, of course, the tricky thing in that, it seems reasonable how you apply convolutions to actually get your so if I know the parameters, it seems not too hard to just apply them to get my outputs. But how do I compute backpropagation with convolutions, right? This seemed really ugly enough as it was last time without this notion of a different operator called the convolution that we don't even know how to differentiate, right? It seems really kind of nasty. So I'll hopefully try to show you that it is not that nasty, actually. And if you look at any code that implements backpropagation, this is why, what I'm going to show you, at least at a high level, is why it's not so nasty. It's because the operations actually are pretty simple. So let me kind of give you a high level of what I'm going to do. So first of all, remember, so we're going to think about layers like this. All right, we're going to think about layers. I guess I'll just write it again. X1 equals fi zi cross wi plus bi. I'm now going to go ahead and just ignore all my channels and everything, because those are just sums, actually, and sums just work like anything else in backprop. They're pretty easy to handle. The hard part, or not even that hard, but the tricky part is handling the actual convolution in a single slice. That's kind of the hard part of backprop here. So anyway, remember that when we had a fully connected layer, this is just a dense layer. This is I plus 1, Ci plus Bi. Remember that for this layer, when we were doing our forward pass, we had to perform this product, right? We had to form that product there. And in our backward pass of backpropagation, what that actually boiled down to was this matrix vector product, Wi transpose times Gi. So it was actually Gi plus 1. That was our backward pass operation we had. If you go back to the previous lecture last time, you'll see that the only way that the weights actually entered the backward pass, ignoring their gradients themselves, I'm just talking about the backward pass in the z variables, or forming these g variables. The only way they entered into it was through this transpose operator. Right? So essentially what you need in order to be able to compute backprop is you need to be able to multiply by a matrix in the forward pass and multiply by its transpose in the backward pass. Right? And those are the two operations we need. So what I'm going to do is I'm going to show you how we multiply by the transpose of a convolution. Right? And in fact, it's not that hard. So let's think about convolutions actually as matrix multiplications. Because in fact they are. They're linear operators. And so we can actually form a matrix product that does the exact same thing as a convolution. Now I'm going to do it here for a 1D convolution, but it ends up being the exact same thing for a 2D convolution. To write it as an actual matrix, you have to apply some nasty Kronecker products actually, but you don't actually do that. You just think of it that way mathematically. So the 1D case is a little bit easier to kind of form. All right, so this operator here, remember what this does is this takes our filter, our weights W, and slides it across an entire vector. So if we have the vector Z, which is, let's say, is an R6 there I had, to Z3, Z4, Z5, and Z6. Okay, we have this. And we want to now form this and the convolution of this and some filter which is in W3 there. I'm ignoring zero padding for now. I'm assuming we don't do zero padding. That would be equivalent actually to multiplying by the following matrix, right? Our first entry here, so the convolution, the first entry of the convolution is going to be, Z1, W1 plus Z2, W2 plus Z3, W3. Right, and the same for all of them. We just slide it over one more, W1, Z2, W2, Z3, etc. But the matrix form of that is just to sort of have kind of this banded matrices that they're called, but really it's just a W1, W2, W3. The rest are zeros. Then you move it over one, W1, W2, W3, 0, etc. Right? That's the matrix form of a convolution. Now, of course, this is a very structured matrix. We wouldn't, and to be clear, we don't want to form it this way. We don't want to actually compute it this way. I'm just running down sort of mathematically what it is. But that's equivalent mathematically to a convolution. And you can do the same thing for a 2D convolution. It's just a little bit hairier. So this is our sort of matrix. This is our matrix form of our convolution. And now the question is, well, how do I multiply by W transpose for that thing? Well, let's just transpose it, right? It isn't that hard. I have on the next slide, but what would it be? It would be W1, W2, W3, bunch of zeros, a 0 there, W1, W2, W3, 0, I don't know how many, I guess zeros there. W0, 0, W1, W2, W3, 0, etc. Right? So that would be my transpose operator. But the important thing to note now is that this is also a convolutional matrix. With the edges chopped off, but it's a convolutional matrix. It's just a convolution with W flipped, right? It has the same block diagonal form like this. It's just that it goes in the order of W3, W2, W1. So this thing here, this W transpose, is itself kind of a convolution. And in particular, if I want to sort of be specific here, it's the convolution of, so if I want to form the inner product of, the matrix vector product of W transpose times some vector Gi, where Gi will in fact be my backward pass variables, that is identical to just zero padding Gi by a little bit and convolving that with what I'm calling W bar there, where W bar is just the W flipped. So it's W3, W2, W1. In other words, it's, again, for signal processing people, it is the actual convolution, where the first thing what we called was actually a correlation. But if you want to call what we did a convolution, you should probably call that a correlation. But it's just a convolution. It's just a convolution against the same filter flipped left to right with some zero padding. And if you zero pad the first one, you don't have to worry about that. You can actually, they're actually okay to do kind of zero padding in both directions. So that's really nice because we can think about doing the forward and backward pass, basically the Wi times it and Wi transpose times it, without ever actually really, of course, forming a matrix like this. That would be hideous, right? If we actually formed this, we'd have a ton of zeros. Even if we did it with sparse matrices, it would still be just ridiculously too inefficient. We do the actual convolution as a convolution kind of numerically, but we just think about multiplying by Wi transpose by convolving with some zero-padded version of or convolving some zero-padded version of the backward pass variables with the flipped convolution. And that's all the backward pass involves for a convolutional neural network. Now it's a little bit, you have to do a little bit more things when you have these sort of multi-channel images. It's a little bit more than that, but those are just additions. Those we actually already kind of know how to do backprop through. We did them with matrix multiplications, and so it really isn't that hard. It boils down to just doing a convolution in the forward pass and a convolution with the reversed filter in the backward pass. And by the way, that all works for 2D also. So in 2D, you just flip it upside down and left to right. Your filter, that is equivalent to multiplying by the transpose. So now we actually do everything we need to run these convolutional neural networks, which are, as I said, really, literally the state of the art in sort of modern AI techniques for things like image recognition, classification, et cetera. So I want to now just mention a few of these applications because I think in some sense, well, actually, I'll first say questions, but in some sense, I think what's made these so compelling is the applications that there are. And so I want to spend a little bit of time on that. So, but first questions. Yeah?
I'm possibly missing something, but should that W bar I plus 1 be a W bar somehow?
Which one?
Under
Oh, that should be, sorry, just W bar I. There's no I, yeah. Was that the other question too? There was? There was another question somewhere. Maybe not. Okay. So what can we do with this? First, a little bit of history. This is not a new idea. This goes back almost 20 years now. Certainly, it was started more than 20 years ago, the research here. Oftentimes, this paper is credited with being one of the first convolutional neural networks, though I think Jan LeCun would say that there was some work even before that that was also relevant. This was a convolutional network for classifying the MNIST data set, which you'll do in your homework. You won't do a convolutional version, but you'll do a fully connected version. And it, for a long time, just was sort of the sole best performer on this task, and despite the fact that it was the best performer on it, people didn't want to investigate this architecture because they just didn't feel like, they felt like it was two tunes or something to this specific task, and so it wasn't really worth pursuing this. And it took about 14 years until there was sort of an explosion in interest. Again, it's very much a simplification there, but there was definitely a lull in interest, and after 2012, sort of an explosion in interest again. But this is sort of the, now you actually know what it's doing here, right? It's applying a convolution. They are not zero padding here, so they actually are shrinking the image every time they do a convolution. They do 6 convolutions. There's 6 channels. The next one, only 1 channel in the image because they're black and white. Then they do subsampling. I think the subsampling is max pooling, but actually it might be average pooling here. I'm not quite sure. I think it's max pooling though. They do another convolution. They do another max pooling layer or something, and they connect it to they concatenate it all together to make a fully connected layer, and then they apply a few of those and have finally the output. And that got less than 1% error on MNIST, which 98 was certainly very, very good. Not surpassed surpassed by a lot of tweaks for a very long time, and still about as good as you can do, because the reality is you can't throw more. That MNIST is kind of tapped out at this point. It's solved by these and other architectures. Let's go into the actual application. Now, this is sort of more history. Let's go about applications. Well, we already saw this image classification problem, right? This is the AlexNet performance. This is a figure from the AlexNet paper. Performance on the ImageNet classification challenge, where, as I said, it sort of blew away the competition, improved by a huge margin over the other ones, and really was what started the interest here. So I want to highlight a few more than this. They're going to, and hopefully getting less and less trivial as the slides go on here, because as amazing as this is, I think a big critique of deep learning has been that it's sort of focused on tasks that aren't that important, like classifying cats and dogs, and hopefully we'll talk about why that is, how that is currently moving forward a bit. But let's start with cats and dogs. One of the most going beyond just sort of these big architectures for specific classification problems, I think one of the more compelling kind of general purpose features of these networks is the fact that actually the features that these networks generate, even when, say, trained on ImageNet or some other classification task, seem to actually be very useful as general computer vision features. So, and those can then be applied even with relatively little data on some new data set. So there's actually a great blog post about this on the Keras website. Keras is sort of a popular, higher level even than TensorFlow or Torch, these things, higher level framework for deep learning. There was a great blog post on using features from existing deep learning architectures to classify images of cats and dogs. So there was some challenge here where the goal was to, you have 1,000 images of cats and 1,000 images of dogs. That's not very much data, actually, 1,000 images of each of them. That's relatively little data. The question was, how do you build a classifier just from that? Well, you could build a convolutional network from scratch. That gets you about 80% accuracy in those two, which is actually quite reasonable. If you run something like a linear classifier, you don't do much better than random chance. It doesn't really work on this problem. Unlike MNIST, say, where you can do okay with a linear classifier, it does quite poorly here. So you can apply a convolutional network from scratch. That gets you about 80%. The other thing you can do, though, is you can take the VGG network. VGG is a very well-known network architecture that was also developed for the ImageNet challenge. Despite the fact that it never won, it actually became a lot more popular than some of the winning ones because it's a very simple network. It uses a lot of convolutional layers followed by max pooling layers and finally a fully connected one in the end. So the idea here, and I actually didn't show it's a 16. Well, there's a 16 layer and a 19 layer version of it, but everyone uses the 16 layer one. So the 16 layer network. And what you can do is you can take that network structure, and the last layers are the ones that sort of specify which class in ImageNet the image is. So all you do is you take those last layers and you throw those away. So you take your exact same sort of weights of the VGG network, and you apply it to these images. You just don't apply the last few layers that actually classify it into one of the ImageNet categories. Which is sort of crazy that this works, because these are features that were tuned in a fully supervised way to predict well on ImageNet. That's how they were learned. But it seems like they do quite well as kind of general purpose image descriptors. So if I take these features from VGG and I apply them to my cats and dogs, and just apply a linear classifier, or actually it might have been a one hidden layer network, you get 90% accuracy. So already you're doing quite well without retraining a network from scratch. In fact, you can't do that here. It works very badly. But just using an existing deep learning network, applying it to your data, and then classifying it does quite well, in fact. And I think actually in a lot of domains, this is what you want to do, especially if you don't have a ton of data to learn your classifier. Don't try to recreate your own classifier from scratch. Just take an existing network and think of it like a feature generator that you can just use and do whatever you want with. Right? Apply a dense network on top of that. It's a very common strategy, and it seems to work really well in practice. The last thing you can do, though, is you can also start at the weights of VGG, but just fine-tune like the last convolutional layer, and that works even a little bit better sometimes. Boy, we're going a bit slowly here, so maybe we've seen Atari games before, right? So maybe I'll skip over that. The Atari game playing, this is Atari, well, I'll let it play as I'm talking. But Ariel talked about Atari game playing. This is a very famous result that Google DeepMind had. Before they were Google DeepMind, actually, they were just DeepMind, and then this led to them being bought by Google. system learning to play Atari games. So this is learning to play Breakout right now. It's sort of hard to see. I wonder, well, yeah, I won't bother too much right now. But basically, it's kind of getting okay after 400 training episodes, I believe. It can like kind of play the game. It doesn't die too often. But then it learns something very cool actually after a little bit after this. But I should say there's a lot going on here. So this is actually a reinforcement learning architecture as well, which is a specific type of machine learning. But really kind of the workhorse here actually is a convolutional network. So it's a convolutional architecture applied to the pixels of that image that's trying to maximize, figure out from the pixels a mapping to controller actions that will maximize score in the long term. So really fundamentally, this is really a deep, a convolutional deep network. So then it learns to like go hit the ball up above and let it bounce on top, which is what humans do when they play Breakout, because you can just sort of sit and relax and let it win for you. This one's actually very cool. Have people seen this before? They're sort of, you probably can't avoid them at this point. They're sort of so annoyingly everywhere on social media these days. And it's only like a year or so old, so it's kind of incredible how popular it's gotten. So this is actually also a great application of convolutional networks that use no machine learning here in the traditional sense. So what they do here, so the idea here is you have some picture, you give it your normal picture, you also give it like a piece of art, and then it will transform your picture to look like that piece of art. So you have like Starry Night on the bottom left here. You take those houses, which is a normal photo of houses, you transform it so it looks like your houses in the Starry Night style. And it's actually very cool what's happening there. So that network is also, or this procedure is also just using VGG. So what they do is they take VGG, the feature descriptors that come from the convolutional layers of the VGG network. Maybe I should actually, no. You can look up what that layer is. I think I didn't actually put it in the slides, but this is a 16-layer convolutional architecture. And they look at only the convolutional layers. So they don't look at the last layer that classifies what it is. They don't care about ImageNet or like what class it is. They just look at the hidden layers in this VGG network. And what they do is they change the input image. They start taking little steps in the input image to make the activations, the particular neurons that get fired, make those look statistically more like the ones in the VGG network applied to the art image. So you have some features that you get out of your art image, and you take actually their inner products with each other to get like the expected values of how often certain things activate, and you change your input image in a way that gives those same activations when you apply it to the input image. Okay, so you're adjusting the input image to make the hidden layers more like the VGG hidden layers when run on the art image. And that's all it is. There's no actual parameter tuning there. It's just fixed parameters from VGG applied to these paintings, and then you adjust your input image to make your image's features more like the features that come from the art image. And that's all it is. And you get these really cool styles that are now, unfortunately, everywhere across the entire internet. And everyone likes to make their images look like, the Scream and Starry Night. But finally, in a little bit more even, this has all been fairly trivial so far, I think. This next one actually, and there's a lot more like this, but this next one just came out actually this past Friday. Google just announced that they have done some pretty impressive work on detecting cancer in radiology, and essentially in node biopsies. So actually, this is not a new problem, right? When we talked about classification, I talked about detecting cancerous cells. That was our motivating example. But back then, we were like, the things we actually had were just 30 feature descriptors that we had manually constructed from these images. This is actually the full process. This is the sort of the real thing, where you're actually just taking the raw image of these biopsies and trying to detect from this image which are the areas of this image most likely to be cancerous. And it turns out, at least according to their blog post, which is here if you want to go to it, they can actually do this better than a lot of trained radiologists with give it as much time as sort of the radiologist needs to look at the image. They're getting something like I forget what exact metric they're using. It's something like a location-based detector, but they're in the high 80s, whereas trained radiologists are maybe in the low 80s when they do this. So maybe they're still not quite at the best radiologists. I think the The claim is that the very, very top people can do better, but on average, actually, they're doing better than trained doctors here. Of course, I think you can argue if maybe it's a very specific set, very well done images, et cetera, but nonetheless, really, really impressive. These are things that seem like they should be automated at this point, right? We should be able to at least assist a doctor by providing them some feedback from these systems. And I think these things, this is going to be the way it's done within 5 years, I think. At least all medicine will actually, or not all radiology at least will use sort of, like, again, just my own guess, but I'm not a radiologist. But I would guess they're all going to use some form of at least assistance from these kind of deep learning architectures. All, again, based upon, convolutions and backpropagation and things like that. Okay, so I only have 20 minutes left. Any questions before I go on? So in the brief time that remains, I want to mention one other type of specialized architecture, which has also gotten a lot of attention recently, called recurrent neural networks. And these I actually don't want to spend as much time on, and I can't because I don't have as much time in class, but I want to spend a little time just giving the intuition behind what these things are, and then you can look on your own about a little bit more information. There's actually a very good blog post on these things that you might want to go through if you're curious and want to learn a little bit more. Okay, so the core idea here is that the models we've used so far tend to focus on kind of independent examples. So each example, each image, each data point was drawn kind of at random. It's independent of all the ones that came before it or after it. This is called the IID setting, which we talked about a little bit from the theory standpoint, which stands for independent identically distributed. So in practice, though, we often want to predict a more structured sequence of things, right? So think about predicting like a sentence in response to another sentence. That's necessarily kind of a structured thing, right? We want to use the structure of the temporal sequences to actually predict things. Or if we use things like time series forecasting, right? If I want to predict how the electricity is going to actually happen, not just the peak over tomorrow, but if actually how it's going to evolve over the next few days, that's also a temporal kind of process. Something like speech to text, right? We should not presume that every sort of block of audio is independent of what came before it, because actually, if you assume that, you can't do speech recognition. It just fails miserably. We as humans use a ton of context to figure out what people are actually saying when we hear these words. So there's really a need for models that can capture the temporal dependence between examples. And the way I'm drawing that right now is in this format. This actually can be thought of as a graphical model for those that know that term, but we're not going to cover those much until next time or until next few lectures, so don't worry about that yet. But essentially what it's saying is that the input at time 2 can depend on the input at time 1, and that leads to the output at time 2, right? So these things are interdependent. They're not independent. They're not IID anymore. And this motivates actually a different type of architecture than what we talked about before, called a recurrent neural network. And the basic idea here is that we're going to model a set of hidden states just like we did before. So as before, we're going to have our inputs x. We're going to have some hidden states z. And I'll actually omit the subscripts here. So we'll just have one set of hidden states here. And then we'll finally predict an output, which I'll call y hat, just because it's going to be a prediction of our y's. And that way we can use separate letters for each of these things. Of course, in reality, these can be stacked. They can be multiple layers of z's. They can be convolutional if you want. They can be all sorts of things. But I'm just going to draw it in a simple case here. So the idea is we have our inputs. And at least on the input side, we're gonna treat them as if they were kind of independent. It's all coming into our architecture independently. But we're going to let the hidden states, the z variables, actually depend both on the input, x, but also upon the previous hidden state. So the key here is that z at time t is some, and again, this is the dense general case, but you can specify that you can specialize this to convolutions or anything else you want. It's going to be sort of a matrix vector product with the x input plus a matrix times the previous z plus a bias term with a nonlinear function applied to that. Okay? So the idea is that we're allowing the hidden layer to depend both upon our input and the previous time steps hidden layer. This is called a recurrent network. And the output is the same form as before. It's just going to be a some function of just the hidden layer. You could have a pass-through that depends on the input too, but we don't usually do that in normal neural networks, so we don't really bother here either. Again, because these can be stacked, so you can have multiple ones. You can actually, in some cases, you can have them going the other direction in time, so you can have them going the other way. If you sort of know your whole sequence ahead of time, you could actually, it's reasonable to have kind of a bidirectional one, so one going one way, one going the other way, but this is sort of the basic model. And the way we train this actually is just by unrolling that network and training it on some sequence of data. So if I think about that, if I take an input sequence, a bunch of x's, right, say from 1 to 100, I can take that network structure and just unroll it 100 times, right? I can just take this network. If I know the parameters, I just take this network, I repeat it 100 times, and I generate some outputs. Right? And that's just a process like a normal feed-forward network. In fact, when you unroll a network like that, it turns out this is just kind of the same thing as a very deep network going, deep in time at least. And then, as before, I'm just going to minimize the sum of my losses over between my predicted outputs and my actual targets that I have. And the key here is that I had the same set of weight matrices for each sort of transition layer in this unrolled network, right? So even though I have, a different set of hidden units for each time, and they all depend on each other in a very complex way, this is just sort of a little bit of math, but it's not that hard. I mean, especially if we use kind of the computation graph form of our backprop, we just get the gradient kind of for free. We just compute, say what the forward pass is, say how the parameters will affect the evolution of all these weights, of all these hidden units, and we can then just compute backprop to get the gradient with respect to those parameters, and we adjust them to decrease our loss function. So conceptually, it's actually identical to how we train a normal network. It just involves this process of looking at some observed sequence that's long and unrolling the network to get all these gradients. It turns out there used to actually be a more complicated way of training these, but this is what people do currently. They just unroll the network and compute gradients that way. There is a few tricky parts here, like how do I find what my first hidden units are? Because there's no hidden units before this, so how do I do that? Well, you can do a lot of things, but it's pretty common just to add actually a unit of all zeros at the beginning. And what that means is your first few predictions probably aren't that good because you don't have enough context to really make them very well. But after a while, that'll kind of all mix together, and you have reasonable context in your hidden state to determine what's going to happen next. You just pick a big enough time frame, essentially. Last thing I'll say with regard to sort of the algorithms here, which is not, again, it's not very much, is that there's actually a problem with these things in the sort of naive way you might implement them. And that is that it's very hard to capture kind of long-term dependence you might have in temporal sequences. So if I'm trying to predict text, for example, and I see a left parenthesis, that probably should somehow change my hidden state to say I'm expecting at some point to see a right parenthesis that's going to close that. Right? A lot of these kind of like parsing things actually fit very nicely into kind of keeping around the context, right? And the context becomes what's stored in the hidden state. But that's very hard to learn, right? Because it can be a really long time before you see, especially character by character, it can be a really long time before you see that closing parenthesis. And so the sort of vanilla recurrent neural networks, especially if you use things like sigmoid activations or tan activations, had a big problem with this for a very long time. It's a problem called vanishing gradients. What it essentially means is that the influence of the past kind of fades slowly over time to the point where 10 or 20 time steps down the road, you've kind of forgotten everything from before, before 10 or 20 time steps ago. So just because gradients, this is all continuous, there's smooth functions here, they kind of disappear. By the way, the normal way of kind of avoiding that in deep networks is these rectified linear units. Those don't really actually work or they're very hard to work in recurrent networks because they have the other problem in that they kind of can blow up very easily. So if you think of a linear system actually and just keep multiplying the same thing by the same matrix in a linear sense, that term can either shrink to infinity or it can blow up. Rectified linear units don't actually deal with that problem. They just, because they're just still linear on one end, they still have the same blowups as before. So anyway, that's all very kind of hand wavy. But the point being that traditional recurrent networks, just this structure, there are some fixes that people are kind of proposing these days, but this structure, stacked at least, has a very hard time learning long-term dependencies. And so instead, people use this very common network called an LSTM for long short-term memory. And I won't want to go into it. You can't even read, I think, in this thing. You can zoom into the PDF if you want to take a look at it. This is actually not even my figure. It's a figure from another paper. But this is a network proposed also in a long time ago, 20 years ago now. Something about 97, 98 was really good for proposing like these kinds of networks that did really well, but then no one really used for a very long time. And then what it essentially encodes, it has a very specialized structure that encodes kind of like pass-through features and explicit mechanisms for kind of storing information or then kind of dumping it out of, putting it to kind of a simple memory or then getting rid of it out of that memory. And so when it's in the memory, it does not change from time to time, and when it gets out, it vanishes. And so it's a little bit more like kind of an actual memory where you would store something into a hidden unit and then you kick it out. And it does that by a very complex process that kind of looks like a differentiable AND gate and a forget gate and kind of these things. But again, I can't, there's not nearly enough time to describe this in detail. So if you're curious about that, there's lots of good resources out there for LSTMs. But they are kind of, there's sort of this black box that's proven, or sort of this fixed structure that's proven very, very effective a lot of times. And people have tried, by the way, to adjust them in various ways. And every paper talks about how they can do better than LSTMs, but no one ever uses anything else. So, because these just seem to be very robust and work quite well in practice. So having said that, let me talk about a few things you can do with these things. Again, quite briefly here, because I only have about 7 more minutes of class. Okay, so the first thing I want to mention is this excellent tutorial that was written by Andrei Karpathy, who wrote a tutorial on RNNs that use a model called a character RNN. And this is basically a predictive model. You can think of it kind of like an autoregressive model, for those that know what that is, where it takes as input, character by character, some text, and tries to predict what the next character is going to be in that text. So the input to this text is the input to this model is letter H. It goes into a hidden layer, but then the output it tries to predict is the letter E from that, right? Because it's spelling hello. So for, only knowing this, it will try to predict E. Then you tell it what E actually is, and you tell it the actual E. It tries to predict the next letter. You tell it the next letter. It tries to predict the next one, etc. So it's always trying to always predict kind of one letter ahead. The nice thing about this is that once you've trained this on some corpus to sort of predict the next letter, you can just start sampling from it, right? So I can just start sampling, given H, tell me what the most likely next letter is, or sample what the next letter should be. And then you take that sample and you feed it back into the network the next time, and it can generate kind of an arbitrarily long piece of text here. But remember, it's doing this character by character. So it's just doing a character at a time is it doing this stuff. And this is actually kind of amazing what it can do, though, even this really simple model. So here is the results. So what I'm going to show you now is I'm going to show you, so he trained this model with different sort of depths and everything on many different sort of corpora, right? Because you can train it on, Shakespeare's works and the output looks like Shakespeare. You can train it on various other things. And one thing he trained it on was the source code for the Linux kernel. So he trained it on the entire source code, all concatenated together in one big file of Linux. And then he had it just start generating code. And this is the code that it wrote. So it doesn't do anything, I should say, but it looks kind of creepily like actual code from Linux. So it puts a nice comment before the code block. It has, a static int indicate policy, like with the right lettering and everything of how they use source code in Linux. It closes parentheses and uses proper indentation. So it actually does, has, if FD, it doesn't have FD, it has no actual context here, right? But if FD equals something, the kernel will blank with coeld to it user space. So it says like nonsense text, but it looks like it could be kind of real. And it has things like proper indentation and kind of really creepy structures that look sort of real. It also will occasionally just stop and put in the GNU license, because when you concatenate all the Linux source together, there's a lot of these licenses, so it will occasionally just repeat that, and it knows that very well, so it's memorized that, so it occasionally just puts that in randomly. Another very cool one is he trained it on the LaTeX source for a algebraic geometry book, and though he did admit he had to fix things a little bit, it wasn't that major, and once he did, he actually got like theorems from an algebraic geometry book, and so you can't really read it here, but it reads like some theorems of an algebraic geometry book. It has, and it will sometimes output figures and stuff like this too, and it has proofs for the theorems it makes. It puts a QED at the end of proofs and things like this. And he did say, I'm not quite sure how much he had to edit these things, because he did say he had to edit this a little bit to make it compile, but not very much. He was able to compile a lot of text from this output. Again, character by character, learning to build sort of parsable LaTeX. It's really quite amazing.
Wow.
So these are the kind of things that kind of make you sort of still amazed at just how ridiculously powerful these models are. A little bit more seriously now, let me just say a real application in the time I have left. So one of the more compelling applications, I think, of LSTMs and recurrent models in general is something called sequence-to-sequence modeling. So the problem with LSTMs, at least for the Karenin, they're cool models, but it's sort of hard to see exactly how you would use that to accomplish something really useful, right? They're sort of predicting character by character, what can you really do? But this model actually was slightly different. So what it does is it's called a sequence-to-sequence model. So you actually give it as input a whole sequence, and it will predict the whole sequence as output. And the way it does this is you put in the input sequence as an LSTM, or a stacked LSTM really, with no outputs. So in the input sequence, there's nothing to predict. And then you feed it an end of sentence tag. And then you make it try to predict the entire response, essentially. So the response should be, some other characters there. And in the response part, you do kind of this feed-forward thing where you do like the autoregressive thing like the Karenin does. And I won't go too much. There's actually some cool examples you can have of like dialogue systems that use this that actually answer questions when you ask it them. But actually, the real application here is that Google's current translation engine uses this on the back end to do their translation. So there's also a great article in the New York Times Magazine recently about this. But essentially, I think it was almost a year ago now, Google's translate engine got a lot better all of a sudden, and it got sort of amazingly good in some sense. And what they're doing is they're actually doing a sequence-to-sequence model where they're having multiple LSTMs running forward and backward, all stacked on 8 GPUs, eventually sent to something called an encoder that eventually goes, says, okay, now stop, and it runs a decoder to sort of encode what the person's actually saying in a different language. And they've done it in a cool way where you can actually, I believe, sort of swap different languages in and out. So it uses the same kind of internal representation, but can translate to different languages too. So there's some work on that, at least, if they're not doing it currently. So it's kind of amazing, again, what can kind of be what can be done here in terms of sort of the power of these models. And the last thing I'll say is, again, this work is actually pretty old at this point. This is also by I didn't have the citation here. This is also by Andrej Karpathy, the guy that made that blog post. This is combining a recurrent network with a convolutional network. So the idea is that this is a system for automatically captioning images. And the idea is you apply a convolutional network to the image. You take the output of that network and apply that to the first layer of a recurrent network, the first hidden layer of a recurrent network, and then you run the recurrent network forward. And what it does is it generates things like this. So you give it this image, and it says, man in black shirt is playing guitar. You get this image, and it says construction worker in orange safety vest is working on road. 2 young girls are playing with Lego toy. Boy is doing backflip on wakeboard. So this is, again, all just from giving it captioned images of other captioned images, learning a convolutional structure, which I think was pre-trained with one of the ImageNet models, followed by a recurrent structure to do things like this in an automated way. So this is, by the way, why deep learning in some sense is so popular right now, is because of examples like this, where it can do things that, frankly, still don't seem possible for a computer to do, right? I mean, even knowing how it works, it still seems unbelievable that it can do that. And I think this is why we're at a point right now where deep learning is so, such a hot topic, and why I think that this will last at least a little bit longer, the excitement here, because we still haven't really scratched the surface on just how powerful these models can really be. All right, next time we're going to switch gears for a bit to talk about probabilistic models, but though we're going to come back to sort of both those together with deep models at the end of these lectures. All right.